Welcome to Study Loop.
So we need to find the moment of inertia of this cone. So we can just draw the cone here. We have a radius from the center of the cone to the edge. We'll actually label this as capital R. And then we have this axis going through it here. And then we have this thickness associated with this cone. And this thickness changes as you go up the cone. So we can say that this is dx. We're going to say that this angle here is going to be considered alpha. And then we have the height of this entire cone. This is going to be considered h, height. And this vertex here, we're going to label this vertex A. As you go down the cone, the radius changes. So we're going to have to model it with radius r, lowercase r. And at this point, we can tackle the question. So we have the mass of this cone is going to be equal to the density of the cone times the volume of the cone. And the volume of the cone is going to be pi r squared h over 3. So we can say that the mass times equals the density times the volume. This is the definition for mass. And this would be equal to pi rho r squared h over 3. Given that the volume of a cone is, again, pi r squared h over 3. So in this case, we would have to solve for rho. So rho is going to be 3m over pi r squared h. So in this case, we can say, okay, let's get a new workbook and say, let's consider one disk of this cone of thickness dx, which we have labeled here in the diagram. And then we'll say at a distance away from vertex A. And at this point, we can say, okay, R is going to be equal to x tan of alpha. So this is where it gets a bit complicated in the sense that we need to find the volume of this piece. So the volume of this piece would be, of course, pi r squared times the thickness, so dx, and then we can plug in for r and say that this is going to be pi x squared tan squared of alpha dx. At this point, we can say that m is going to be equal, the mass of this cone is going to be equal to rho times pi x squared tangent squared of alpha times, again, dx. The moment of inertia of this cone, is going to be the mass times the radius squared divided by 2. And at this point, we can say, okay, if this is true, we can plug in for our mass, and we have rho pi x squared tangent squared of alpha dx all over 2 times x tan of alpha squared. That would be our radius term. And at this point, we can say that I is going to equal rho pi of x to the 4th tan to the fourth alpha dx all over 2. And at this point, we can integrate. So we can say that I is going to be equal to 0 to h of rho pi tan to the fourth alpha all over 2 times x to the fourth dx. Now this is only because we have dx here. So in order to find the true moment of inertia, if we were to integrate this from 0 to the full height of the cone, we can essentially find the moment of inertia with respect to x, where x is, again, that thickness. So we simply have to go through the full length, integrate the full length of the cone with respect to x, and we would find the moment of inertia. So this is going to be rho pi tan to the fourth alpha divided by 2 of h to the fifth over 5. And we can say I equals rho p over pi rho divided by 2 times r to the fourth over h to the fourth. And this is given that tan of alpha equals r over h. This is from the cone. This is a given from the cone. So if we know that this is a given from the diagram of the cone, we can substitute this and say that this is going to be r to the fourth over h to the fourth, and then times h to the fifth over 5. And this is going to be equal to pi rho r to the fourth h all over 10. At this point, we know that rho is going to be equal to 3m over pi r squared h. So at this point, we know that I is going to be equal to pi rho r to the fourth h over 10 times, and then rather, let's erase this row. We're erasing this row because, of course, we're going to substitute for rho. And rho here, it's 3m over pi r squared h. This h cancels out, this pi cancel out, and we are left with 3m r squared all over 10. So this would be the moment of inertia of this cone here. And that's the end of the solution. Thank you for watching.